Hello, good morning. So today we're looking at a specific perspective on linear functions, looking at their formula. Right? Remember the four perspectives we have on functions? We had what? Words, tables, formulas, and graphs. So the four perspectives. So we're going to be focusing in on the formula perspective today, and one in particular called slope-intercept form, and then two supporting concepts called the vertical intercept and the horizontal intercept. So slope-intercept form is a huge idea. It's widely used. It's probably the most commonly used form for linear functions because it's super useful. And the reason is because you can judge a book by its cover, which is what we want to do as humans. You're not supposed to, right? But that's what makes this useful, is because with a slope-intercept form, you can judge a book by its cover. You can tell everything you need to know about this linear function from this form. And if it's not in this form, getting it to that form will tell you all that same information. So that's the power of what we're looking at today. So, you've probably heard, or you might slightly remember or tremble in fear when you hear the words y equals mx plus b. That is what we're talking about, but I don't want you to just remember the letters. I want you to understand why it works, how it works. So, the formula for linear functions, the first and not the only perspective. I want to say that there's lots of perspectives. This is just the most widely used one. Doesn't mean it's the best tool for the job all the time, is the slope-intercept form. Okay, and just right out the gate, I want us to be thinking of these things. That slope tells us the change, and the intercept tells us the starting point. So I'll give you an example to motivate this here. So let's say, for example, we'll just kind of go through a little exploration here, that I was given a tree as a gift, that it started at 5 feet tall. It's like a little sapling or adolescent tree, and it grows 3 feet per year. So this is a good fit for a linear function. I'm going to say yes. Why am I saying yes? Because it has a constant rate of change. How fast is it changing? 3 feet per year. Every year, 3 feet. Every year, 3 feet. That's a constant rate of change. So this is a linear function. Has a constant rate of change of 3 feet per year. Or we could say, it's constantly growing 3 feet per year. So yeah, it's a good fit for a linear function. So let's generate a table of values. So let's say, t equals 0 is the start. And we are going to say here that height is a function of time. Right, or that height depends on time. So if we say time in years and height in feet, well, we'll start at 0, and we know at time equals 0, we were at 5 feet. After 1 year, we've gone another 3 feet, so it's 5 plus 3 equals 8 feet. After 2 years, we've gone 5 plus 3 plus 3, which is 11 feet. After 3 years, start at 5, added 3 for the first year, 3 for the second, 3 for the third year. So that's 9 plus 5 is 14 feet. You might be able to see the pattern here. This should be 17. This should be 20. So this is a constant rate of change. We're adding on 3 each time we go up by 1. Right, so that tells us our delta H over delta T is 3 over 1. And we're seeing that. The change between each of these is 3. So it's a good fit for a linear function. Now, how would we write this? Based on a input-output relationship. Well, H needs to be a rule based on T. And so what's really happening? Well, H equals f of 0 was just 5. H equals f of 1 was 5 plus 3. Oh, I changed that here. H. Height as a function of 2 years was 5 plus 3 plus 3. The output for 3 is 5 plus 3 plus 3 plus 3. Plus 3 plus 3 plus 3. And this, well, I don't want dot 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 there because it's just those 4. But what we see here is we're having this repeated addition, and each time we're adding 1 more on, right? And so really, what is this? This is 5 plus 3 times 2, right? 3 plus 3 is the same as 3 times 2. That's 6. How many 3's do I have here? Well, I've got 3, right? This is the same as 5 plus 3 times 3. How about here? This is 3 plus 3 plus 3 plus 3. It's 5 plus 4 times 3. Oops. Don't know why that keeps happening. And I don't like it. 4 times 3. And so what are we seeing here? That we're starting with 5. That stays just as it is. And each time t goes up by 1, so here's, let me do this. 1, 2, 3, 4 for t. We're seeing it started here with, oh, I'm seeing my t value here, 2, here's 3, here's 4. And so with this first one too, we could see this as being 3 times 1, right? Because I'll just get back 3. So then for any t, let's do it one more time just to really drive this home. For f of 5, our last one, we know that should be 5 plus 3 plus 3 plus 3 plus 3 plus 3 for those 5 years. And that equals 5 plus 5 times 3. So then really in general it should be 5 plus what times 3? T. For any t, it's going to be 5 plus t times 3, that rate of change. Or another way to write it would be 5 plus 3t. We don't need all the brackets. So what's nice about this, we just generated this formula, and make sure that how we did that makes sense to you. Notice that, after 10 years, I would like you to try this yourself. What would you expect f of 10 to be? And make sure that you see that it is 35. Okay. So what we did here is we generated this formula from kind of first principles thinking, what we knew about the problem. And then what we ended up with was this formula that has stuff that we should recognize, right? And what do we recognize from this? We recognize that this 5 was what? Our starting value. And what was this plus 3? That's right, it was this constant rate of change. It was this 3 feet per year. And this is what we call slope-intercept form, or intercept-slope form, because what's here? The constant rate of change, we know that's called the slope for linear functions. So we have the slope, and we have the starting height. This is what we call the vertical intercept. In general, it's the name, right, for whatever your starting value is. It's not always height. And so since we want to be as abstract as we can in math, we say it's the vertical intercept, or where your output starts. Starting output. So we got our starting output and our slope. So what I'm trying to tell you is, even if I just gave you this now, this function, you could tell me everything there is to know about this function. Oh, it started at 5 feet. It gains 3 feet every year. It's right there. You can judge a book by its cover. So let me drop another quick example on you here, and I'd say, what if I had a second tree, and I told you that its h was also a function of time, and it looked like this? What can you tell me about this tree? So take a moment and think about it. Hit pause. What do you know about this tree? What did it start its height at, and how fast is it growing? Initial height is 10 feet. The growth each year, 6 feet, right? Per year. And we'll say increase, just to be clear, because it is positive, and that does matter. Right, the slope being positive or negative, we know that matters. So the initial height was 10 feet. The growth each year, an increase of 6 feet per year, constant rate of change, tremendous. And again, what this means in general, this is what we call the vertical intercept, or where it starts as a point on the graph, means that when t equals 0, h equals 10. So as an ordered pair, that's the point 0, 10. That's what we call the vertical intercept. It's that actual point where it crosses the vertical axis, because when the input is 0, that's where you are. Right? Let's draw a little graph of this thing. So here's x and y. Or this is t, because we're not with x and y, we're with t and h from an input and output, right? So time and height. So when time is 0, we started at a height of 10. So we should start right here. And this is what we call the vertical intercept. And so for most problems, aka initial value. Because if this was a cost problem or a profit problem or a population problem, it's the starting value. So here was the starting height, but it could be the starting costs, the starting population. It's a general idea of where it begins, where the function starts, when time equals 0 or when the input equals 0. I will say a little caveat here, and you'll come up against this in your practice problems. Not always meaningful. Right? When the input is 0, what that value is doesn't necessarily make any sense. There's times where we can't have an input of 0, right? Like when we divide by 0, or rather when we try to divide by 0. There's times where it just doesn't make sense, right? And so we don't want to, we don't worry about it, right? What would it mean to have 0 people working on this project? Well, that's not something that we really care about, so the vertical intercept wouldn't mean anything. But it often does, so that's why we take some time to talk about it here. But in general, it's the initial height, it's that output value, and it's a point on the vertical axis, on the h-axis. And the growth each year tells us we have a increase of 6 feet per year. So I'm going to move this stuff out of the way here. Whoops. One nice thing about having the not actual paper, even though I miss it, is that from 10, we have an increase of up 6 feet over 1 year, right? So up 6 to 16 and over 1. So it looks something like this. Up 6 over 1. And that tells me the next point, which is 1, 16, 2, 2, 22, and etc. And what we get is a set of lines, or a set of points that gives us the line. And this would continue in the other direction too. But we know here this delta h over delta t, that's steepness, that's 6 over 1. And that's how we can generate the next points, right? If this is the rate of change, it's going to tell you what the next points are going to be. It tells you how it changes. Up 6 over 1. So what I'm trying to tell you is that there's only 2 things you need to know about a line. This is why they're super useful, is because they're simple. There's only 2 things you need to know about a line. A point, a singular point, and its slope. Remember, that's the constant rate of change. And this is any point xy. It could be the vertical intercept, or it could be any other point, because as long as you have the slope, you can take a point and then use the slope delta y over delta x to get your next one, whether it be positive or negative slope. All right, because here's some xy, here's some x plus the change in x, y plus the change in y. Okay, but what I really just want to say here, not to get bogged down in notation, is you just need to know 2 things, a point and the slope. And if you don't know the slope, all you need is 2 points, because then you can go find the slope, right? You can find the slope between those 2 points. So you just need to know 2 things. It's very, very simple. And so that's why this form is so useful. So slope-intercept form, let's write it out formally here. So y as a function of x is equal to b plus mx. And again, it looks exactly the same as we did with the tree problems, where b is your vertical intercept, 0b, and m, and I'm going to include the sign here because we remember that the sign matters. This is the slope. You know, your delta y over delta x. And so just to kind of give you that concrete example we had before, it was what 5 plus 3t? That's in slope-intercept form. Okay, and so the vertical intercept there was 0, 5, and the slope was 3 over 1, or just 3. So that's coming from here, and this is coming from here. So hopefully that's clear. So what's good about this is that it's a very strong property about lines. And we say a function is linear. In the math language we say if and only if, which means if you have one, then it definitely means the other, right? If you're Sean Malley, then you're definitely a math professor, is not the same as if you're a math professor, then you're definitely Sean Malley, right? What this is saying is that if you're a linear function, you can write it in b plus mx form, or if you can write it in b plus mx form, then you definitely are a linear function. So a better way to say this would be like the CEO of SpaceX is Elon Musk. I don't know if he still is or not. Right? So the CEO of SpaceX is Elon Musk, and Elon Musk is the CEO of SpaceX, right? So they are if and only if, right? It is both directions. So anyway, a function is linear if and only if you can write it this way. So I'll ask you, is this linear? So if I have a function that looks kind of maybe close, is this a linear function? Well, I'm not quite sure, maybe just looking at it. There's a lot going on. We got brackets. So how can we tell? If you can write it in b plus mx form, meaning if you can rewrite it as b plus mx, it's linear. So this is a way to check. So, all right, let me do some rewriting. Let me do some simplifying here. So f of x equals, I'm going to distribute that 3 in, and I'll get 3x. 3 times a negative 4 is minus 12, plus 2x minus 1. And I'll combine some like terms. 3x plus 2x gives me a 5x. And then a minus 12 and a minus 1 gives me minus 13. So is this in b plus mx form? Yeah, it's in mx plus b form. Isn't that okay? Mx plus b is the same as b plus mx, right? So yeah, this is good to go. What's my b here? Let's judge this book by its cover. b equals negative 13. Remember the sign. What's my slope? Slope is 5. This is the delta y over delta x. It's 5 over 1. So I know everything I need to know about this line, but the point was that it didn't necessarily look like it, but this thing is linear because I can write it in mx plus b form. So yes, it can be rewritten as this. How does this look on the graph? Again, we're going to get more into the graphing later, but if the vertical intercept is negative 13, that means we're down here somewhere at negative 13. The slope is a positive 5 over 1. So it means I go up 5 over 1, up 5 over 1. So negative 13 up 5 is negative 8, 1. So the next point I just generated using the slope is 1, negative 8. Over here this was 0, negative 13, the vertical intercept. And the next one over would be up 5 over 1. So I'd be at a x value of 2 and a y value of negative 3. I just added 5 here to here to here. And so then I can get a sketch for this line because I have enough points to see the rest of this relationship. But we're going to dive into the graphs more in the next section. But that's all you need to know about the line is the starting value and its slope. So one final note on the vertical intercept. Okay, just to kind of really be clear about this. The vertical intercept is the value of the output when the input equals 0. Right, what do we know about this point? The height up in the air is a distance of b, and the distance side to side is 0 because it hasn't gone left or right at all. It's on the vertical axis. That's why it's the vertical intercept, right? But big idea here is it's the value of the output when the input equals 0. We know that we're on the vertical axis. It's also called the y-intercept. But we don't always use y, right? We use h or p or whatever. So then there is a corresponding idea of the horizontal intercept. And it is the kind of mirror image of this. It's the value of not the output, but the input when the output equals 0. So if we look at this graphically, horizontal intercept, this means intercept, where do you cross? Horizontal, the horizontal axis. So here we'd be looking at some point like this. It's the value A when the output is 0. So it'd be somewhere like this on the horizontal axis. Okay, so sometimes this has meaning and sometimes it doesn't, just like with the vertical intercept. And I'll give you an example of how that works. Okay, so we're going to do 2 examples at once. We're going to be kind of crazy here. So let's say I've given you a formula. It's in b plus mx form already. Okay, and this models a population of Mathsville, P, as a function of time, t years since 2010. Okay, so that's P of t. First of all, let's just take a look at this and judge a book by its cover, right? Since it's in b plus mx form. This is what? Our initial value, right? This is our b, vertical asymptote, vertical intercept, not an asymptote. That is something different. And then here is our constant rate of change, or our slope, right? And then same thing down here with example 2. This is also in b plus mx form. If it wasn't given to you in that form, try to get it there, right? Because we know that that's what makes something linear. And we see same thing here. Okay, this is my vertical intercept, right? 0, 500 is my vertical intercept. Here 0, 1000. vertical intercept, and then my slope, m, is -4. Here it was -20. Okay, so first of all, we know just from the form of this thing that the vertical intercept is right here in yellow for each. But I want to do this in the general case because sometimes it's not always written this way. So find the vertical intercept. So for example 1, the vertical intercept is when the input equals 0. So for example 1, that's P of 0 equals 1000 minus, what was it, 20 times 0? Times 0, right, where 0 is my input. And so what are we left with? 1000, as we should be. So we know that 0, 1000 is the vertical intercept. For example 2, again, input equals 0 is going to give me my vertical intercept. And my function was Q of P equals 500 minus 4P. So then Q of 0, when the input is 0, that gives me 500 minus 4 times 0, which will leave me with 500. So then that tells us that the vertical intercept is 0, 500. Now how about the horizontal asymptote? Did I say asymptote again? Intercept. I'm working in pre-calc and algebra at the same time. Intercept. Intercept. Where it crosses the axis, right? So this is when the output equals 0. We're looking for the input value. Right? For the vertical intercept, we're looking for the input equals 0. What is the output? And then we'd find it. So here we set the output equal to 0 and we solve for the input. So for example 1, again we had P of t was 1000 minus 20t. We said set the output equal to 0. Right? P of t, this is the output. Set it equal to 0 and then solve for t. So then I have to use algebra here, and that's fine. Or you could use your calculator. Subtract 1000 from both sides. So we get negative 1000 equals negative 20t. Remembering to bring that sign with it, right? Always look to the left. And then we divide by negative 20 on both sides to solve for what the t value is, what the horizontal value is when the input's 0. And so negative 1000 divided by 20 is positive 50. So then the horizontal intercept, is 50, comma, what's my output again? 0. That's what it is for example 1. What were the units here? 50 years, 0 people. So we might have a sense of what this means already, but let's peek back to example 2. Q of P was, what was it? 500 minus 4P. So when the output is 0, we want to know what is the P value. So again, we're going to solve for P by subtracting 500 from both sides. We get negative 500 equals a whole negative 4p. And we divide both sides by negative 4 or multiply by a negative 1/4. And we get p is, well, 500 divided by 4. Oh, you guys are going to make me think now. 125. Not that bad. Not too much thinking. So 125. So what is this? This is the p-value when the output is 0. This is the horizontal intercept. This is where the graph crosses the horizontal axis. Okay, so the question is, what do each of these mean? What do they mean? And I had someone comment in the discussion once and said, you know, I'm taking a math class. I didn't expect to be writing so much or explaining in complete sentences. That is a key part of this course, and it might be very different for you. But we do need to explain, what does this mean in plain English, if it means anything? So for example 1, we had P of t, this was 1000 minus 20t, where t is in years. Years since 2010. P is population of Mathsville. So the vertical intercept, we said this was 0, 1000. 0, 1000. Input is 0. P equals 1000. So what does this mean? This means that, and you see how I'm kind of going a layer out. All right, this means t equals 0, p equals 1000. What is t again? This means after no time has passed, or you could think at the start, which really means in the year 2010. And then over here we've got p equals 1000. What does this mean? 1000 people. So this means that there were 1000 people in Mathsville at this point. So now we kind of take this more concrete idea and this more concrete idea and string them together into a sentence. So you see how I went from like the abstract out to the notation and then out to the concept and the details, right? That's the power of math. Because we can work with this stuff. Out here though, you can't really do any computations on that or do any problem solving. But we can talk about what it means, and that's just as important. So what this means is, in 2010, that's taking this first part, 1000 people lived in Mathsville. So that's what that vertical intercept 0, 1000 means. And how about the horizontal intercept? Well, actually, let's go back and do the vertical intercept. Wow, keep goofing those up. Vertical intercept for the other example, which was Q of P equals 500 minus 4P. P is number of people working on the job. Q is the number of hours it takes to complete. So then the vertical intercept we said was what, 0, 500, and again you can see it, it's right there. But 0, 500, so what does this mean? Input P equals 0, output Q equals 500. What does P equals 0 mean? P equals 0 means there's 0 people working on the job. Q equals 500 means it takes 500 hours to complete. So again, now we kind of join these two ideas together if it makes sense. And so we see when 0 people are working on the job, all right, that's this piece. It takes 500 hours to complete. So my question to you is, does that make sense? Which is something you should constantly be asking yourself. Does that make sense? We got 0 people working on the job. It takes 500 hours to get the job done. No, that doesn't make sense. We can't have 0 people working on the job and have it get done. So here, no, having an input of 0 people doesn't make sense because you need someone working on it, right? Now you could make up the argument, well, maybe it's a computer program that's running and we need people to speed it up or something like that. Or there's a robot doing the job. But really, no, this doesn't make sense in this context. So don't be afraid to say that. And you also need to pump the brakes on your brain to be able to see that. So no, this doesn't make sense. This is, or we might say, not meaningful to interpret. This is how I'd expect you to kind of phrase it. Since we can't complete the job with no one working on it. Okay, so here's an example of where the vertical asymptote means something and where it doesn't. It doesn't always have to. I said asymptote again. You guys, I'm going to have to put a little note in here that says, don't listen to me when I say asymptote. Intercept. It makes way more sense when we say intercept because it's where it crosses the axis. So I apologize. Need to make more coffee. But here we go. Intercept. On the horizontal axis, this is when the output equals 0 and the input equals some value. So for example 1, we saw the horizontal intercept for P of t was what? We had it at 50. Horizontal intercept was 50, 0. So what does this mean? P equals 50 and our, not P equals 50, you guys. T equals 50. P equals 0. All right, after this I'm going to pause and make coffee. So T equals 50, P equals 0. What does it mean? This is a pair. That T equals 50 is 50 years after 2010, which we could even take that a step further and say that's really meaning in the year 2060. All right, so this is kind of our thought bubble coming off of that. And then P equals 0. What is P? Population is 0, which what does that mean? No one is living here. Again, I'm coming up with these kind of quick, but this takes a little bit of thought to get there. And now we see these two ideas are really paired together, just like this is paired together. So this tells us to interpret this as in the year 2060, Mathsville will be abandoned, or there will be no one living there. So again, taking it from the notation out a few layers to the actual application of what it means. And for example 2, let's see if this means anything in this context. So it was 500 minus 4p, and we had the horizontal intercept of, what was it? That's vertical, 125.0. So what does this mean? What does this mean? P equals 125, Q equals 0. Well, P equals 125 means that there's 125 people working on the job. And Q equals 0 means it takes 0 hours to complete the job. So this is what this value means, and this value means, and again, that means that we're pairing this with these ideas. So this means that if 125 people are working on the job, it will be completed in 0 hours, which means instantaneously. Doesn't make sense. Here I didn't even ask if this makes sense because it kind of did. It just kind of rolled off the tongue. It does make intuitive sense. There's going to be no one living there in the year 2010 and 2060. And you could even make an argument for it. Well, there's probably some people that are going to stick around, but this is what the data supports. Over here, 125 people are working on the job. It'll be completed in 0 time. That doesn't make sense. Of course, there's going to need to be some time spent to complete it. So this is my 2 examples of showing you when interpreting the intercepts makes sense and when it doesn't. And again, just to give you a graphical perspective, and we'll look more at this next time, how this first one would look, it starts at a population of 1,000, and in 2010, right, on the t-axis, this is like 2010, t equals 0. And then after, 50 years, we know we're down here, and there's no one living here anymore. And so the graph really looks something like this, a steady decline, a constant decline, where here's my vertical intercept, 0, 1,000, and my slope, my delta y over delta x. Well, we know that from the formula it should be what? Negative 20 over 1. We're losing 20 people per year. So that's all right here. And you can judge that book by its cover. And for the project one, Q and P, the number of people working on it, from 0 to 125 people. We said the vertical intercept was 500, the number of hours. Here, this is the number of people. So this is 0, 500. This is 125, 0. And now you have everything you need to know about this line. You've got 2 points, which you can get the slope from. But we also know the slope is negative 4, which means down 4 over 1, right, as my delta y over delta x. Okay, so just to give you a few perspectives there, you could also go to a table to verify, right, that over time you should have for this first example over here, starting at 1,000, then 980, 960, 940, etc., 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 as you keep going forward until 0. But the main points from today. What is the vertical intercept? What is the horizontal intercept? Can they be interpreted? Does it make sense? And just because it might be challenging to interpret doesn't mean that it doesn't make sense. It might be a bit of a walk. So don't just discard it if it's not super clear. But sometimes it just doesn't make sense to interpret them as applicable. And then the other key thing here was that you can write any linear function in slope-intercept form, right? B plus mx. If it's a linear function, you can write it like this, even if it looks different. And when you have it written like this, you can then judge a book by its cover. You know the slope, and you know the vertical intercept, 0b. So you'll have some practice problems tackling this from different perspectives, graph problems, algebra problems, etc. But hopefully this will be fun and exciting for you, and now you kind of are armed with this tool of what y equals mx plus b really means and why people care about it. It's because you got all the information right up front. So enjoy practicing. We'll see you in the class discussion.